Well, hello everyone. We'll go ahead and get started. Let me go ahead and open us up in prayer, and I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course, Lord. I pray that the material that we have in this course and everything else that they're studying are all going to help them get the future job or company of their own choosing as they proceed towards finishing their degree. I pray, Lord, that you would also help them in their spiritual formation, Lord, that the times that they're able to study scripture, that they'll be taking that all to heart and they'll be able to get proficient in how you can be ascertaining theological principles that we can generalize and use in our day-to-day life. And finally, Lord, give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, we have been covering a lot of interesting information, and so I'm going to get into our next chapter, which is internal memory. But since it's a Thursday, I'm also going to be focusing a little bit more time on our project-related efforts. And so we had a little bit of an excursion talking about digital logic. And so I'm going to pull up our digital logic um, application, and we can get a chance to see if there's any questions on that. Another thing is make sure everybody orders your Arduino kit as soon as possible if you haven't already, because we want that to be seamlessly getting into what we're going to be doing in our project development. So I'll get into the internal memory discussion in a second, but I mentioned that I have this greatest hits section, and we've covered enough material now where maybe it might make sense to just quickly go through that and think of what we've covered. Stalin uses the von Neumann architecture, but he also throws in the system bus, and he could show how we can be drilling down. And so this is going into the CPU, and we see that there's some similarity in structure between a von Neumann architecture and what's seen in the CPU. But then below that, we have all of this other level of detail that we're going to get into a little bit. But for now, we're just trying to be focusing on the main elements of a von Neumann computer. Here was an example of a card that can fit into a motherboard with some of the kind of different characteristics. And so this is for a two Intel quad-core Xeon processors, so a little bit more of a server rather than a desktop type of configuration. And there's a lot of interesting features that are on here. One of the things I'll mention, because we're going to be talking about memory, is here is a term DDR3 1333. And so this 1333 indicates the clock frequency that this memory can operate. And we're going to get into getting a sense of what this DDR means in just a few minutes. So we saw these different trends that are starting to take place, that the transistor density is still increasing, but the frequency that the clock rate can go is kind of leveling off. The power that you can get in a density, you can't keep increasing that, so that's leveling it off, or else you're just going to melt all the electronics. And so another thing that started to go up now is the number of cores. We're going to be getting into this whole idea of how a computer works in more detail. We can see the von Neumann elements here, the memory, the I/O, and the CPU. Now we're getting a little bit more insight by looking at the different registers that are inside the CPU, another form of memory. And so some of these names will become a little bit more familiar to you. Here is a general way that a computer works. It does this fetch execute. We've also talked a little bit more about how it can be doing interrupts and then get back on board. We can have more details that we'll unpack of more layers of thinking about the fetch and execute cycle, but that's just a high-level view of that. We then started to think about the memory, the different types of memory, what is used where. And so up on the top of the pyramid, it's the fastest. And so registers in the CPU, that's very fast. we have cache, and our last lecture, we spoke about that, and so we had a little bit of a sense of that. The main memory here, we did see this term DDR DRAM, and so we'll get a chance to start to unpack those terms. We'll get into solid state memory as well as a little bit more historical regular hard drives, and there's other types of memory as well. What we see in Stalin that they use a fair amount of time going over a lot of studies, and so this is an example how they could see that there is this bell curve for both instruction and data, but it's a little bit different in terms of what would it be its mean, and so the location that tends to go to for instructions in one part of memory, the place that it goes to in terms of the overall memory for data is slightly different, and we can see that type of a characteristic. There's different types of memory usage, and so random is more the kind of things that we would be seeing for this data. The sequential is a little bit more of what you would see for instructions, and those are a couple of things. We got a chance to be thinking about cache. There was a time where there wasn't any, and then through analysis, they started to see that performance can go better because cache actually is faster than the main memory, and so you can actually improve the overall performance. And then, well, if one is good, maybe more is better, and that's what is the case. And so for systems in the laptop and desktop, it's using 3 levels of cache is common. And there's various ways that you can be controlling the cache. And this is where I'm going to go into the next chapter in detail. And we saw that this type of things that we can be doing with cache, it can get fairly complicated. And so we got exposed to some of those things here, all of these elements. And I tried to just do a quick survey of getting a chance to be thinking about that. But what we're going to be focusing on today is the internal memory. And so this is like the random access memory. That's going to be the main thing that we'll be focusing on. But there's more to it than just having memory. We want to be thinking of the different technologies. And so there's random access memory, there's read-only memory. How are we going to go about doing the packaging, the addressing, and all that? And then we get this idea of error correcting. Guess what? Transmission of information is not perfect. And so this is another way that we can improve overall performance, that if there's an error, we can detect it and then correct it and then keep going on. We'll get into some specifics looking at IBM and Intel using this type of technology that we'll explain in a little bit. Here we have this DDR DRAM, and we have these 2 different types of RAM. We have SRAM and DRAM, and so we'll get a better sense of what that is and more complicated information here that we'll see in a little bit. You can have flash memory, and it's very common to be using NAND. And so some of you may remember when we talked about these different types of gates and an OR, and then we had this other type of gate called a NAND and a NOR. And then there's also some new non-volatile solid state memory technologies. And just to give you an example, with some of the research I've been doing in neuromorphic computing, resistive RAM, that's what this stands for, it has some interesting properties that gets a little bit closer to the way our brain deals with memory, because it not only stores the information, but it stores the context, the emotional state, and so it tempers what actually happens when you're doing that store or retrieve. So here are the 2 general things that we do in memory. We either write, so we have a cell of memory and we place something in it. So you select it saying, yes, we want to allow new data coming in, and the control line is going to be there, or we can have the sensing, and so we're just reading what is already stored in that memory. And so there's these different types of memory. So now we're getting a chance to see some of these acronyms spelled out in case you're not familiar with some of them. Random access memory. And so you can do read and write, and approximately it takes the same amount of time to do both. It's not exactly the same amount of time for some types of memory. And so that's something to keep in mind. Read-only memory, it means you only can read it. So you burn it once and then it's going to be like that forever. There's also something called programmable ROM. And so what this is, it's a little bit more reprogrammable so that you can set it and it acts as ROM, but say you made a mistake, you can go back and fix it. And something that's even a little bit more able to be changed is erasable ROM. And so yeah, so there's just a degree of relatedness between these three, and you can then have something that you can, it may be a little bit more difficult. You have to like shine UV light to erase it, and then you can reprogram it. Those are all possible. And then you can have flash memory, the kind of things that you have in a USB drive, something like this, which I'm sure that you guys are familiar with, that are quite handy and widely used. So now we have these two main types, the dynamic RAM. And so the information that is stored there is on using a capacitor. And has anyone heard what a capacitor does? Is that something that you're familiar with? You can just do a thumbs up if you're familiar with that. So some of you have heard about it. I'm going to take it that maybe others haven't. Folks that are engineers in the class probably have had an encounter with what a capacitor is. Well, I'm going to show you an illustration of that in the next chart, and I'll explain it a little bit. And so so static means that it's going to be, you have it there, you don't have to keep refreshing it. And so that's going to be the difference. So DRAM is actually less expensive. And so it's a even the way they describe it here, it's a storage capacitor. You can put charge on here, and actually you can have it store information as a result. But what's going to happen, the capacitors slowly lose the charge. And so that's why you need to refresh it periodically. Now, I'm not going to go through this circuit, but these are transistors. These are the electric symbols for transistors. And so some of the engineers in the course probably have already had some encounters with this. And so you can count this 1, 2, 3, 4, 5, 6 transistors are here. There is some other interesting things like this circle means an inverter. This is something that we saw with some of our quick tour so far, looking at the logic gates, but I'll just point out those things. So that just gives you an idea. This is a lot simpler. It only takes one transistor. You can see for an SRAM, it's going to take a lot more. So this is going to be more expensive. And so thus, if you can get by with using DRAM, that's going to be saving you money, and that's a useful thing to do. So I mentioned this static SRAM, it's going to be able to maintain that charge. And so just as long as the power supplied, but it's not going to be slowly losing what it was there before. So they're both volatile. The dynamic RAM, it's simpler, it's dynamic, it's less expensive, but you have to refresh it periodically. Versus the static RAM, it's faster, and it takes more electronics to make it happen. And so this is commonly used for cache. So thus you remember cache is supposed to be a little bit higher performing than your regular memory. DRAM is what you're going to be having in your regular memory, and then you just have to have a refresh cycle to keep it in the state that you want it to be. Read-only memory, it contains a permanent pattern of data. And so parts of your BIOS, have you heard the term BIOS? Some of you guys have played with computers. Do a thumbs up if you have heard the term BIOS. So not the majority, but a few of you. With the greatest hit charts, I did a reminder that a motherboard will have a piece of read-only memory that gives it a fail-safe that it can be checking out the hardware and do some initial configuration of what's going on with the motherboard. And so that's what it's a built-in operating system that is at a very low level to give you some sense of checkout and initialization of what you want to be doing with your system. Then we have a more, the next more flexible is programmable. So it's less expensible. It may be written into only once. And so you only have one chance. And if you blow it, then you're going to have to go ahead and find another chip. And so that's the reason why in an earlier chart that I was showing you, we get these more sophisticated here, like an erasable PROM or electrically erasable PROM. How much variability do you want to be able to reprogram that? And the answer is it depends. It depends on your application, depends on what your how much access you're going to be able to have with that chip. So we have read mostly memory, and so we have these options, a PROM, and so you only get one chance. EEPROM, you can reprogram it electrically, erasable. It can't be written at any time without erasing the prior contents, and so thus you have a little bit more flexibility in Flash. It's not quite RAM. You can rewrite to it. It's just like with the thumb drive that I already showed you. You're going to be using this, but it's mostly you write to it, and then you're going to be sharing the information you have in that contents with somebody else. So we have a couple of charts that we're going to be getting some perspective on what a memory module looks like. And so you have the ability to read and write. You have to be addressing that information that you want to be reading or writing. And so here we see some of those things here are the addressing. And here we see the timing and the control coming in. And so those are just some of the things that you can read more about it in the textbook. Here we see a couple of different sizes of chips where it shows you how it's put together and what's here. So here we have the address bits. It goes up to just quick scan up to 19 bits for addressing what is inside this memory. And then we have this data bus that we can put things in. So this is 8 bits. And so 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 bits of memory that's being put in here. There's also some control signals. You need to be applying power. And so that's one. Now this is something that, so this is a 1 megabyte times 8. Here we have a 4 megabyte times 4. And so we can see since it's only 4, then we only have 4 data bits. This is 8, so we had 8 data bits. There is the addressing bits that are here. And so there's some more complexity here that I won't get into, that this is a lesser number of pins. But it actually has more memory, but it's half the width. It only has 4 versus 8 bits on the other one that's listed there. So if you have more bits in your memory address register, you're going to be able to address a larger block of memory. Does that make sense? And so Here we have 9 and 9, and so we're using these for different parts of what we're trying to accomplish here. We have 8 bits, and so here this is like a 1 bit of those 8, and so we're going to have 8 of these things here, aggregating it together to get this 256 kilobyte memory organization. And so if you were to click back and forth, and this is a 1 megabyte, this is 256. So how many to go to 1 megabyte? What is the factor between this and that? Anybody want to venture a number of what that is? So roughly speaking, if I divide 1,000 divided by 250, what number is that? You be following what I've got there? Right, yeah, so it's a factor of 4. And so 2 to the 2 means you'd have to have 2 bits. And so that's the reason why there's an extra 2 bits here versus just having this number of bits. So I just wanted to give you an idea. That's how you create larger memory, and you want to address it all, so you're going to need more address bits. So hopefully you're catching on what I'm trying to have you think about in that regard. So here we see interleaved memory. So closest in, it's composed of a collection of DRAM chips. It's grouped together to form a memory bank. Each bank is independently able to service a memory read or write request. And with K banks, it can service K requests simultaneously. And if consecutive words of memory are stored in different banks, a transfer of a block of memory is sped up. So here we can see all these different banks of memory that we're seeing here that we can be aggregating together. And so that's just one of the things that's starting to happen, what's going on inside. Okay, we had this topic in this chapter where we wanted to be thinking about how we deal with errors. And so there's 2 types of errors: a hard error. This is something that if you've ever heard the term the blue screen of death for Windows, it means that you have some a hardware failure, like one of your sticks of RAM. I'm going to show you more details about this, but this is an example. It's an older example of a stick of RAM. Say like you have some a transistor or something failed. This means that needs to be replaced. That's going to be difficult to deal with, but a soft error could be a random non-destructive event. You get your power, maybe it went dim, or somebody turned on the microwave while you're using your computer and there wasn't enough filtering. And so these are the things that can happen, or your power supply is getting a little bit worn. Those are the things that could cause that. So here's the general idea. We have memory coming in, then we have some additional bits that are used to compare that. And then if there's an error, you want to be doing fixing that. And so you can look in the textbook for more detail. And so you have these, this is using one type of error correcting code, is called the Hamming code. And so you have these bits here that you can then determine a parity. And with that, here you can see that there's no errors, and then you can make a decision that, yes, here are the bits that we have. But what if you have one of them that is wrong here? And so with this Hamming code, you can determine that that is an error, and then you can make that adjustment. And so you're still propagating the right information. And so this is like a 1-bit parity check that you can be fixing an error in your data. So what this means, if you're increasing, if you're doing error correction, you're going to have more bits allocated for that. And so this just gives you an idea of the kind of increase that you could have depending on how many check bits that you're going to be using. This could be an example of a configuration. So every fifth or fourth bit is a correcting bit or something like that. And so here we have 12 bit positions and we have 4 that are correction bits. So that fits into a byte of 16 bits. That's would be one possible way of doing an error correction code. You can have more elaborate kind of schemes that could be done, and Stalling gets into this as he does in most everything, just like we talked about cache, where there's a lot of different error correcting codes and strategies. And so this is just one that gets into a little bit more detail. So here we're seeing an example with 2 errors that the single error correction does not work. It can't figure out how to deal with, it could fix one of them, but it can't fix both of those. And so thus we're going to need more error correction to handle this. And so approaching it with more complexity, saying like what we're trying to consider here would be something that we would have to do in this kind of a scenario. Okay, here we have some of this advanced DRAM organizations. And so SDRAM is one of the most critical system bottlenecks when using high performance processors as an interface to the main internal memory. So that is something that's out there. And so here we can have our main memory. We're seeing some challenges that are going along. And so this SDRAM here stands for synchronous dynamic random access memory. So it's a DRAM, but it's also gives a little bit more specifics about it. The traditional DRAM chip is constrained both by the internal architecture and by its interface to the processor's memory bus. But a number of enhancements to the basic DRAM architecture have been explored. The schemes that currently dominate the market are SDRAM, so that's the synchronous dynamic random access memory, and also this DDR, which stands for double data rate. And so if you have this DDR SDRAM, that would be the kind of thing that you're going to be seeing on a spec sheet for a piece of memory module. And I'll show you an example of that. So SDRAM is one of the widely used forms of DRAM. It exchanges data with a processor synchronized to an external clock. So thus you have to be in sync with the processor and running at full speed of the processor memory bus without imposing a wait state. With synchronous access to the DRAM, moves data in and out under control of the system clock. So it's like you have a conductor, that's the clock. And so the CPU and the memory are all doing things at the same data rate. And so that's something that we have here. Well, we'll see some complicated charts here. And so this gives you an illustration of what a 256 megabit synchronous DRAM looks like. And you can see some similarities to what we were showing on some of the other charts when we were looking at a package. We can see the addressing scheme. We can see the clocking and command signals that are going through here and then pass through the internal constructs of the chip. It doesn't show the 16 wires here, but here is the data going in and out into these different memory cells. And so here it's actually the packaging inside of it. It's composed of other lower level, smaller bits of memory. And so you have 16 megabits. So 16 times 4 is one of the ways that we're trying to aggregate getting this up to the desired number of the overall memory that we want to be putting into this one chip. So here are some of the bid assignments. I mean, what the acronyms are, and then spelling it out. This is getting a little bit beyond the focus we're going to be talking about, since we're trying to have this more as an overview perspective in a course, but that's something that you can be thinking about. So everything needs to be synchronized with the clock. And so here we can see how things are done. So you have a read, and then you have the data coming out a couple clock cycles later, and then you have this no operation. And so here it can take several clock cycles for the data to start to come out. That's something that you need to know about. It'd be nicer if it was faster, but things only go so fast, and so that gives you an idea of something that's going on. Well, for microelectronics, there is something called this Joint Electron Device Engineering Council, and I've had some colleagues that have been part of that. So this double data rate SDRAM, it was developed by JEDEC, the Solid State Technology Association, to have a standard that the industry would agree upon, and so everybody can make their own memory chips, but they're all using the same type of technology, so they're interchangeable. And so that's what I'm just trying to point out by this chart. Here are some of the characteristics. And so here we can see DDR1, 2, 3, and 4. And so it has this another term, prefetch. And so this is using some perspective from like what Stalling has quoted a lot of studies that, hey, if you do some of these things, you're going to actually improve performance. And so prefetch, there's a buffer here. And so how many bits are in that buffer, and you can see that it goes up depending on what level of DDR that you have. And so the front side bus data rate, the clock speed that's going towards the CPU, we can see it's going higher and higher. So DDR3, this gives you this range. DDR4 is even higher. And so that's a perspective on that. Here we can see the DDR generations. And the engineers in the course probably are familiar with these. And so a mux is basically a combiner. It sticks these things together. You can have a mux feeding into another mux. And so these are going at lower data rates, but then you put them all together, and then you can have something going at a lot faster data rate. That's what we're trying to show here. Rather than being limited by this, you put two together, and that gives you the potential to be nearly doubling the data rate that's being passed through. You're using one module at a time, and so you're kind of offsetting where they are, and so you don't have this lag that we saw here, because you have multiple banks of memory that you're activating to help out with giving your throughput to be going a little bit faster. Okay, I'm gonna step out of the lecture note charts for a minute here, and I'm going to show you a couple of things. First, I'll show you this this picture here. It's actually for the purpose of the class, this is probably going to be a little bit easier for you to see as compared to me showing you this with my webcam, but this is the same thing, but this is a blow up. You can see 1, 2, 3, 4, 5, 6, 7, 8 chips. And so similar to what we saw in this previous chart. Oh, I went backwards. Let me go where we were. No, okay. Where we can start to have smaller subsets of memory inside that's what we see with this is we're using 8 here, and that just gives you an idea what's going on. And this is older memory, but it's still SDRAM, SDR. And so remember we have the terms for that. So the synchronous dynamic random access memory, and then the DDR is a double data rate. Well, this isn't a double data rate the way it's listed here, but it still is this synchronous dynamic RAM. And this just gives you the ideas of what it can do. It can handle different clock speeds. So those are some things that you can see. There's several different related items in terms of the size of memory that it can have. And I'm not going to go through this in much detail, but if you were to go through this spec, it's going to be showing you probably a lot more information than you might want to know. But this looks similar to the figures that we have in our lecture notes, just to give you an idea. So it has that same kind of a concept here. They have various types of things that fall into this family. Here we can see things at the chip level. And so you can have the address lines, you have the data lines, other control lines. All of those are seen in the package. And sizing information. Some of the voltage information, the minimum voltage for things to work, how much current it's going to draw. And so there's just lots and lots of information here. Some of the clocking relationships, and we saw one example of that in our lecture notes. So yeah, I just wanted to just spend a little bit more time to give you a perspective on that. Does that give you some more insight into memory in terms of things that you have in your computer? Give me a thumbs up if you're tracking with what I just shared. Okay, good. So like I said, in this course, we're going in the kitchen. We're getting a chance to look inside, and some of this can be overwhelming. And so one of the things as a computer science or engineer, we have to be trying to take a larger perspective and say, I may not understand all of this, but there's a higher level abstraction where I can get a better sense of what is its purpose. And then I can get into those details to the level that I find appropriate for what I need at that moment. So maybe you just need to get more memory in your computer, and that's all you need to do. But sometimes you actually have to buy 2 sticks of memory based on its technology, because they're meant to be going in synchronous. And so that is one of the terms that we saw, that SDRAM is an example where that can be a requirement. So here we can be seeing the layout of memory for an IBM Z13 server that's focusing on storage. Lots of cache here, L4 cache. Just giving you an idea, these numbers are large, still larger than what you would see in a desktop. Well, actually not anymore, since we're into the gigabyte range. But anyway, it just gives you some perspective on things. But this is at the cache level. This isn't at the RAM level for a computer. So this is still, relatively speaking, are pretty robust. Here it just gives you an idea of the EDRAM in an Intel Core. So this is looking inside a chip. And so that's some perspective there. We have flash memory, so I've already showed you one of those. So very common, very easy, very handy. And there are a couple things that where now we have this EEPROM, and so that can be what can be the guts that are used in the flash memory. That's something that you have here. So this just shows you basically a flash memory. It stores the memory, but it doesn't need to maintain electricity to keep it going, and so it needs to have some way of retaining that charge without any external power. So you have the power come in, it sets a charge, and then it maintains it. When it does a read, it has to send that charge in so it can read the state that has been recorded in a piece of memory. And so this is what we can see for a 1 state and a 0 state. The difference is this charge that is accumulated into the microelectronics. So we can see the structure for a NOR versus a NAND. And so we can see that there's two possible ways that we could be creating a flash memory with those digital gates that we've had some exposure to. And this is just shows a spider chart, just showing a comparison of which might be better to use. And so having them go out farther is better. So you could say that that the NAND is going to be performing a little bit better. The cost per bit is going to be lower. And so thus we can see that memory tends to be using NAND gates for processing that. So we mentioned this at the very beginning, these different types of memory. And so you have a static RAM. So it provides rapid access time, but is the most expensive. You have DRAM, which is cheaper, denser, and slower than SRAM. You have hard drives, which is a magnetic disk. We have those as are things that are out there. But so we can think about these different points that we've got a chance to be thinking about a little bit. So we've talked about SRAM, good for cache, DRAM, good for our RAM, a NAND flash is good for, say, something that we're going to be having with a thumb drive, but it's also moving in the direction where there's a blurring of the line of what's in a hard drive and what can be done with flash. And so we're going to be talking about that a little bit more as we go. But this resistive RAM is a technology that's operating in this regime. PC RAM, I'm not going to be talking about these in detail, but this is an example of a new upcoming technology that are in different parts of this memory pyramid that we've had a chance to be introduced to. This just gives a little bit more background of what is actually going on. What is the overall physics that is leveraged for these things? So you have this spin transfer torque RAM, SST RAM. And so it's a new type of magnetic RAM. So it either maintains one magnetic state or another. Another one is a phase change. And so it actually changes the phase in the semiconductor in a region, and it's able to hold a charge that way. And another one, it just increases the resistance. And so it either has a high resistance or a low resistance. And those are two ways that you can be storing a state. So we, in a nice survey sense, have covered a lot of ground, getting a chance to be thinking about what's going on with internal memory. Let me go ahead and pause and see if there's any comments or questions on what we spoke about. And if there's no questions, just give me a thumbs up that you're tracking this. Let me just kind of get around the virtual room feedback.
I have a question.
Yes.
So what's the difference between the hard drive and the flash drive?
So we're going to get into this as we have the next couple of lectures because we're going to be talking about the hard drive and the external memory. And so that we'll get to that on next Tuesday. And so we got introduced to NAND memory when we were looking at charts like this, or we had it come up a little bit earlier. Let me see if I can quickly back up to. So these are just gives you some general ideas of what's going on in the memory. And then there was one other chart. I'm trying to find it here. Give me a second. Yeah, well, I'll just go back to this chart. And so the a NAND is, you probably heard of a solid state drive, SSD. You heard of that, Nathan?
Yeah.
Okay, that's using this kind of a technology. Hard drive is using disk platters, and it's something being written to that disk. We're going to get into that into the next lecture. And so that's a distinction. There's a little bit of blurring the lines because SSDs are becoming more prominent, and hard drives are becoming more of a technology that eventually will probably go away or just have a smaller, an even smaller utility in the overall storage market. But that just gives you a perspective there to be thinking about those two. Okay.
Thank you, Professor.
Okay. Well, let's click over and see how's it going with your get this out of the way. How's it going with your digital logic? But before I do that, I'm going to go to Canvas for a minute and pull up a link to remind you, if you haven't already, to order your Arduino kit. And I'll put it in the chat for you guys. So project resource information. Here's an example of a starter kit that you can use. So how many people have ordered their Arduino kit? People, have you got those going? I'm only seeing a few, so that's not encouraging at this point. So if you haven't already, please click on that link, and that can give you an example of one that I'd recommend for what you use in this course. Okay. Um, Paul, I'm familiar with the ESP32, and as long as you're using the Arduino interface, I don't know how much you have with that in terms of electronics, a wiring board and stuff like that. And so the answer is maybe it might be fine, but I also wanted to make sure that you're able to do some example projects where you can be adding LEDs, push buttons, a few types of sensors and stuff like that. Okay, but you can let me know. Okay, so anybody having challenges with the digital logic circuits? Putting those together? I'll just have a blank canvas here for the moment here. So, we have these components, and so if I just hold my mouse on that, you can see these different types. And so we spent a little bit of time, I think it was last Thursday, talking about these, the and, the or, the not. Those are the ones that are what I would focus on in the beginning, but we had just some discussions in our lecture for today. We talked about the NAND and the NOR. There's also the exclusive OR, and then there's an inversion of the exclusive OR. Those are all different possibilities that we have for digital logic. And that's what I wanted to have you guys to create. And so let me see if I can get a volunteer or two. Tell me a little bit about your project, what you would like to accomplish with your digital logic programming. And let me see if I can help you flesh it out if you haven't already figured it out. Anyone want to volunteer? Otherwise, I can just select at random, just get some perspective from one or more of you all. Isaiah, why don't you tell us about what you would like to program with your digital logic? And let's see if we can start to flesh out what that might look like. You can
Just one of the project ideas was like a temperature sensor that you could put into a boiling pot. And once it hits boiling point, it'll make a beeping sound, so that the user doesn't have to stay in front of the pot the whole time.
Okay, well, let's think about, so you have a boiling pot and you're trying to have a temperature sensing. And so what I've tried to mention to have people do is have a minimum of 3 inputs that you're going to be aggregating it together. So what do you think would be what we could use for those inputs, Isaiah? Any thoughts on that?
I'd say maybe like an on-off switch to see like if the sensor's in there.
Okay.
And then the temperature sensing would be another one. And a third one, I'm gonna have to think about that one, but pull up my document.
Let's see if I can. The simulator works pretty well, but sometimes it is a little bit quirky. So let me just kind of. Let me move this. Start over. Components. Want an input. So okay, so we have a basic input, and so we have on off, and then we have temperature. So Isaiah, let's think if we can come up with another component that we can be putting in here that would be useful for us to be thinking about. So first of all, I'll just be hooking this. So we have another. Okay, so we have on off, we have the temperature threshold. And we want to come up with another one. And so I'll just throw out something, but this is just something that you could be thinking about. So do you have the do you have the thermometer in the water or something like that? So it could be a diagnostic kind of thing that you could be leveraging. Does that
Right.
make sense?
Yeah, I've actually looked it up. In my one of my last projects in, I think, circuits or something. It's the
Mhm.
DS18B20 waterproof temperature sensor, and you can just stick it in, submerge it into water. And I think for the third output, that could be like a failsafe. So maybe set a timer, because like if the temperature sensor fails, at least there's like an estimate of when it'll reach the boiling point, and so that the user won't just leave it completely unattended.
Yeah, I'm trying to remember how to add a annotation on this, but you could label these inputs. But I'm not going to try and do it real time. So it sounds like Isaiah, you've thought that through, and so this could be your first digital logic circuit, something like this. Um, but this is something that we had just two AND gates, but this also kind of shows you, I was trying to give you a little sense with what I had in the other figure. You can have things that are not just the output that could still be useful information. So this might be something that you could be doing, but another thing you want to be thinking about, Isaiah, is that would be like your first of three circuits. So where would you want to go with that in terms of programming more sophistication is and think about that some more. Maybe you might have to be some more things like, well, your temperature, so what is actually in the solution? Is it water? Is it salt water? Is it water with oil of some sort or some other type of mixture? And so then maybe that would be another thing. It's like you're trying to get some simple way of thinking about what's going on. So this is fairly basic, but you can be using a fair amount of abstraction to be figuring out what it is that you're trying to do with this logic. It's a little bit like a state machine where you're trying to have it, you're programming states and what are the inputs that's going to cause it to go to one state versus another. So anyone else wants to give us a sense of what you would like to do with your digital logic? I'll just randomly select one other person. Grace, any comments that you would like to share about what you want to do with your digital logic? You can either go in the chat or go off mute, whatever you'd like. Yeah, I'm not hearing you. So maybe you're having some comm challenges there. Connor, any comments or questions? What are you planning to do with your digital logic?
Honestly, I'm kind of in a place of just still brainstorming on what I want to do.
Mhm.
Yeah, I'm just kind of still thinking about it.
Well, I'm not trying to put people on the spot, but tell me what your project proposal idea is. and maybe I can help you to frame that a little bit.
Okay. Well, I was thinking of doing something like I was just a bit confused on the instructions of that. So was it just one idea that has all the components, like the digital logic gate, the assembly design, and the Arduino? Capable? Is that like one big project, or is it like three separate projects that tackles each individual?
It's three separate projects, but there
Okay,
is some relatedness between the three.
gotcha. Okay.
So, for example, stuff that you did with a digital logic could then be to some level of to some level be something you would be doing in your Arduino kit.
Mhm.
So you could be fleshing out just the electronics, but you're not having to play with any hardware here.
Mhm.
The assembly language is just getting you familiar with how you manipulate directly with a microcontroller or processor. So what
Okay.
is your general proposal idea?
Well, I was thinking, in terms of like the scope of like the Arduino and stuff. Like I have a general idea of like something that I would like to build um with the Arduino, and that would be like maybe um something that could be useful around the home.
Mhm,
So maybe like a simple alarm clock or
mhm,
something. Um yeah, maybe like a simple alarm clock, or like a screen that shows maybe like the current weather and the current time. Um so that's kind of the idea with the Arduino that I have.
Well, let me just show you how this could start to be playing out with
Yeah.
circuits. Okay, so you want to be woken up at a certain time. So that could be
Mhm,
one thing.
mhm,
Another one could be, well, you need to have the clock charged.
mhm,
And you have to make sure that you're in the right time zone, or if you have, daylight savings time,
mhm,
something like that. So thus is um, is it configured properly? And so maybe you have those configuration ones here that are set for this AND gate. And if it's true,
mhm,
then you know it's ready to actually perform its function of wake you up at a certain time.
mhm,
And so then when that clock is at that right time, 6 o'clock or whatever, it's going to give you a valid output. It's time to get up. So this just gives you an idea of an abstraction of the logic of how you're doing, what is the states that you're going to be in. So it's either it's ready to pass on that time value or not, or is it not configured properly? So
mhm,
then how would you go about doing that for the Arduino? Then it gets, once again, it's like, what level of abstraction are you going to use? How much hardware do you want to be investing to be creating that? It's going to be up to you.
mhm,
So if you wanted to be having a counter and it has LEDs that shows you that it's able to count and add, that might be something that you could show. Um, you may have to get into the details of the Arduino of what it can or can't do
mhm,
and what you're able to put together within the context of this course. But
mhm.
have you purchased your Arduino kit yet?
Yes, I have a kit. So
Okay.
I have it already. Yeah, I'm just like for the context of this class, like are we doing each project like, because I know in the project proposal we have to have like a project for each individual, the digital logic, the assembly, and then the Arduino. Um, did you want us to do all three of them, or like I'm just like kind of confused. Like, or do we combine all of them into one big project that we do and we like submit at the end of the course?
Well,
Like, we utilize all.
the digital lockage is trying to do some, if you want to call it risk reduction for your control logic.
Uh-huh.
Your Arduino, once again, it could be related to an alarm clock, but now you're gonna actually be building something, cyber physical environment that could actually do something related to an alarm clock. In the assembly language, you could be looking at, passing information back and forth between registers and a counter. And so it's actually able to count up. And you're able to show that in the console. It's able to count up to,
Okay.
say, 1 to 10 or something like that. You can see how all three of those are still related to the same theme that you mentioned, alarm clock.
Yeah.
That would be the overall project, but it's broken up into these elements.
Mhm.
So you have the
Okay.
original proposal that fleshes that out. Then for the three particular projects, you actually get into doing some modeling or coding. And then at the end, you tie it into a final report, or what did you find out from each one of those things? Does that make sense?
Yeah, I think I'm understanding it. So I could, if I really wanted to, like make them all correlate into one big
Yeah.
project, right? Okay, awesome.
Yeah, it's meant that they do to at
Okay.
least some degree.
Gotcha.
Okay,
Okay.
that's the goal.
Okay.
Okay,
you.
what I'm gonna stop sharing my screen, and I think that's a good breaking point for now. I'll look forward to see you all next Tuesday, and God bless you all. Have a good rest of your day.
Thank you, Professor.
Thank you so much, Professor.
Take care.